Thank you. Just to check, can everyone hear me at the back? Give me a wave if you can hear me. All good. Perfect. Okay, so it seems there's one or two more of you than there was present in my bathroom mirror when I was practicing this talk. So you'll have to excuse the nerves a little bit. So my name's Ian Anderson, and I work with Seinjuti at InMobi. We're a mobile advertising network. We're a mobile-first network, and we wanted today just to share some of the work we've been doing building out location-based social graphs. And so this is some work which is kind of like it's evolving, and so we wanted to really kind of just to provide an overview of some of this work. And so I'm going to give a little bit of background, which isn't really kind of a full-on data science, but it'll help you understand the work which we've done at a later point when we actually start to talk about these actual kind of social graphs themselves. And then I'd like to just share towards the end of the talk a brief update of how we're actually kind of rolling out Spark throughout InMobi. I'm not sure quite how many people would have actually heard of InMobi, so can I have a raised hand if you have? So there's a few. That's good to see. But we actually are much bigger than a lot of people kind of imagine. So we actually reach 1 billion unique devices every single month. And I'm not sure quite how clear these numbers kind of can show up. We actually have quite a substantial presence over on the kind of the JPAC region, in addition to where you might kind of expect in the North America and EMEA. And so, data sciences, just a little quick recruiting note, we actually have data sciences opportunities pretty much all over the world. So we have a data science lab just down the road in San Francisco, some in the UK, we have someone in Winnipeg, so all over the place. So if you are looking and interested for work, please do get in touch. So as a kind of mobile advertising network, we have a notion of a series of actors. We have a publisher, and that's someone who owns a kind of mobile web property or a mobile kind of application. And so their view is that you have some very hard-working application developers, and they want to kind of monetize, and so they can continue to invest in the kind of the games, the applications, and so on that are typically provided to users for free. And so we have that kind of set of people. And then we have the other set of people who are the advertisers who kind of wish to meet and kind of connect with certain people and make them kind of aware of their sort of propositions. So there's a few of the publishers there that we kind of work with. And so one of the goals within data science is a kind of a notion of a disappearing ad, if that makes sense. And it's quite a strange thing to say, but there is a perception here, a perception in the industry that people are like, ads are evil. But if you actually kind of start to kind of break things down, if you actually provide an ad which has some kind of information that kind of complements what someone's trying to do, you reach the right person at the right time, then this is kind of blurring that kind of occurs. And suddenly, ads can become perceived in a different way. They're kind of perceived as information and kind of complementary. So there's a number of kind of different formats which we kind of show on here, and you've probably all kind of encountered similar ones. But our view is, from a relevance point of view, is to try and kind of make something that's complementary to what the user's trying to do, what they're trying to kind of see. And this is almost just a kind of a qualification piece as to the kind of why we're here. And so this was, we're very fortunate that we're kind of growing significantly all the time, but we actually serve about 6 billion ad requests every single day. So we have a lot of data kind of flowing through, roughly 250,000 kind of Hadoop jobs are kind of running. And this is all coming from the billion unique devices that we see. We actually kind of try and, in order to sort of build up this the relevance side of it, we actually end up processing a lot of data every single day. So although we kind of generating about 24 terabytes of new data, we're actually kind of processing and updating about 500 terabytes every day. The other thing as well is, and I'll leave this slide there more for something that you're interested after this talk to kind of dip back into, we try and make sure that we contribute to open source projects. So the one that we should probably today is the Apache Falcon, which is basically a data management and process orchestration platform, and so allows us to kind of express independencies between different kind of jobs, so things can kind of run in a sort of seamless manner. We get the right data at the right time. Just in order to kind of understand the data that's sort of flowing into our network, you have to think that our goal is not to kind of target an individual user. We don't really kind of care or want to know about the behaviors of an individual user. We're actually kind of looking for groups of behaviors, so things where it may be kind of business travelers as a segment, people have a kind of interest in kind of games and so on. And so what we're going to show today is how we kind of build up those kind of classifications of these groups of devices using kind of location data as a kind of membership criteria. This is just a very brief overview of almost the setup. So just to check you can still hear me okay. So we have this kind of feature generation pipeline that's running, and so we have a series of kind of pig jobs which are using kind of Falcon, and they're kind of extracting various features which we can kind of build into our kind of models that end up in the HDFS store. And then we have our Spark jobs and Spark applications, and there's many others which we don't show here, but just for the purpose of this talk, we're going to look at these three. But really, to try and understand the talk, we're going to jump to the end and show you almost like an output, and then explain how we did this. So kind of everyone's familiar with the kind of social groups where you have some kind of bond, whether it's people you went to university with, a film club, and so on. Membership criteria for being part of that group is dynamic. There's some kind of collective sense of unity. For today, we're thinking about location, and so you could say like people who go down to the kind of the Levi Stadium. I always thought it was a Candlestick Stadium, but I mean that's changed. They have this kind of shared membership, and so they have this kind of shared group. So if we start to think about the sort of data which we get, what we're showing here on the screen is a series of red markers. So when an ad request gets sent through, optionally sometimes we're also sent location via the publisher, always with the user's consent. Now, as you can see, location data is inherently noisy, and so we have various algorithms we can run, something like a convex hull, which you could imagine is like trying to stretch an elastic band around all of the kind of the outer red points, and you can then weight it, and that will kind of give you the kind of the blue marker in the middle there. And the reason why we want to have multiple points arriving from a user is that if someone was on a train, they're going to kind of go, oh, look, here's a location request, and they send another one in 30 seconds time, and you end up with this kind of data. But that indicates the user was at these locations, but the reality was they may have been traveling at sort of 70 miles an hour past the Starbucks, so they weren't there. So once we have this kind of notion of a POI for a particular user, we can then start to build out these kind of segments. So we're going to sort of zoom in on the green markers and locations that are shown there represent places where a user's journey originated from, and the red is traveling into San Francisco to visit POIs, which indicate a kind of a professional place of work, a sort of employment, could be for coming in for business meetings. And so for every red icon that's shown there, there's a corresponding green one that kind of comes out. And so here we could then say, now we want to, there's a kind of shared collective group behavior between these people all kind of traveling in, and we could start to actually kind of show some ads which be relevant given that sort of behavior. And I'm now going to pass over to Seinjuti, who's going to talk about how we actually kind of start to assign these labels and start to understand what these places actually kind of mean.
Can you hear me? So everybody has a smartphone these days, and there is a location service running in the background of the smartphone, which is kind of trying to triangulate your location based on GPS coordinates or based on Wi-Fi connections or iBeacon technology. And once we have this location data, what we want to do is to understand the kind of point of interest it represents. And that brings us to a POI classifier that we have trained in Spark. So the problem we are solving is, given a geographic location, for example, a country, can be United States, United Kingdom, India, we want to understand the nature of the location, the point of interest, and that helps us to enrich the context of the ad request during service time. This particular talk tells us about 7 classes that we have trained against, Typically, they can be a public terminal, like an airport or a railway Amtrak station or a bus terminal, hotels or inns, eateries, sports center, places you go for tennis or swim clubs, community centers like public libraries, academic institutions, or retail stores. So these are the 7 classes we are talking about here. And once we attach a label to a POI classifier, that helps us kind of profile the user as either a commuter, or he's a frequent flyer, business traveler, university student, or a retail therapist. So we started to use the decision tree model in Spark, and right now we have up to 70% accuracy for predicting a kind of POI. So we use 70K labeled locations for United States, and we used this to classify about 500K locations or public Wi-Fi connections, and then build profile of the users who were present in those locations. To give you a little bit of flavor on the features, this is not the entire list of features, but a little bit of flavor. So we are looking at ad request distribution across these locations throughout the week for a month. So the day of week and the time of day is an important feature, but absolute numbers mean nothing, so we had to use ratios. So the ratio of weekdays to weekend traffic was really high for university students, because they're engaging more in the university locations during that time. Whereas for eateries, there were peaks around hours where you basically go for dinner or lunch or breakfast. Whereas if you see the average hour spread of the requests coming from hotels or inns, it's kind of the highest. That's the min hour and the max hour, because usually frequent business travelers are present in that location in the early hours of the day. They go to work and they come back and are present again in the late hours of the day. The other kind of features we used is repeat visits, how many devices continuously engage with a certain location, and the marked difference were noticed between universities and airports, because usually airports will see a lot of devices for a very short period of time, whereas universities will be seeing a fewer number of devices over a longer period of time. Some of the parameters we used, this is Spark 1.2 and 1.3 versions. We built a decision tree classifier with a 30% test set and a 70% training data, and then we moved on to the random forest, which is showing more promise using 13 decision tree ensemble methods. What we haven't done is a 10-fold or k-fold cross-validation, and as we are going through the Spark conference, we are learning that those APIs are already available in version 1.4, and that's showing more promise for sure. So this is the first model that we built, and these are some of the F measures or accuracy, and it is doing relatively well in the 4 categories where we have a lot of labeled data like universities, inns and hotels, eateries and stores. Whereas for community centers, sports and fitness, and airports, we have a class imbalance problem. So these are underrepresented, and so out of the box, we didn't have a solution to solve the class imbalance problem. That's the confusion matrix, which is leading up to the numbers that you saw on the previous slide. Once we use the random forest, though, we are getting a much better performance in the same 4 categories, but the underrepresented classes still show a low performance numbers. So we wanted to contrast this case with a base model which uses Weka J48 decision trees. And the most important feature that we got there was MOT, which kind of oversamples your underrepresented data, and that causes an equitable distribution of classes. And as a result, we got a slightly improved performance. And therefore, we are looking at using the APIs to build out this MOT feature inside Spark so that it can improve the random forest models. So in a nutshell, the comparison here shows that this was a proof of concept model for United States focusing on certain regions. And we are getting an overall accuracy of 60% in decision tree Spark. Random forest gives us 69%, and a baseline Weka model gives us 70%. But the good thing is, when we want to scale it to millions of location data that we are collecting in 1 billion devices, Spark definitely stands out. without sacrificing much of the accuracy. And in fact, in certain categories like university, and it's actually giving 68% precision rates over a 65% rate given by Weka. So a couple of visualizations here, how we are doing. The diagram that it's showing, the picture that it's showing up here, you can see Hilton San Francisco Union Square, that's where we are located. And it's predicting a lot of locations which are hotels, the yellow marker around it. Do keep in mind the location service actually gives you a certain radius of accuracy, which can be up to 100 meters. So it's not exactly at the location, but within 100 meters of the location. So it's doing a pretty good job detecting a lot of hotels in this area, which is kind of true. Similarly, it's able to detect from the Wi-Fi connections, the public Wi-Fi connections, that it's and the features that the devices exhibit in these locations. The pink markers show they are clearly airport terminals. The green markers show it's a university area, and as you see, it's a UCSF kind of the university itself and different kind of buildings inside the university. A lot of eateries again here. There's some lounges, cafes, Thai cuisine, so looks decent to me. The blue markers show stores. So the algorithm is predicting stores, and if you zoom in, you will see it's the Westfield San Francisco Business Center, which indeed has a lot of stores inside it. So, so far so good. We have points of interest. The classifier is working pretty well. Now, we want to take the next step, which is connected components of these POIs. What is a connected component in this case? It's a set of locations which has been frequently co-visited by users over a period of a month. So it is based on the frequent visitation trends between locations, and we used the graphics libraries to build these connected components out for United States, and it gives us around 5,265 components for 500K locations. And this took just 2 hours to build the components, so it's a lot of promise that we can scale it to different geographic areas. So what are the vertices and edges in this case? So the locations of the POI that we kind of learned in the first step becomes the vertices, and the users who are moving between these locations become the edges. And instead of doing a correlation, it's actually doing a connected component, so it can give you more than case of 2 or case of 3 kind of connections. And once we have built out these connected components, we rank the users inside them using some of the user features, the amount of engagement the devices have shown in those locations, and we are able to profile those users using the connected components. I hope you can see this. So this is an area zooming on Baltimore, where you have the Johns Hopkins University and a couple of community colleges. So the green markers show the universities. The red markers show eateries, in this case Starbucks, Applebee's, Whopper Wi-Fi, Panera Bread. And there are a couple of target stores, or 3 target stores in which these students have traveled. So it's fitting nicely with the segment of university students who go to stores, go to eateries, take the Amtrak connection. The pink in the middle is actually an Amtrak station. Similarly, over Hayward, there is Hayward University, a couple of schools which we mark as green, and then we have a lot of public libraries which are green color, wherein these students are going to study, and a couple of eateries, fitness centers, and so on and so forth. So these are both good university segments of devices. The next one shows the business travelers who are coming into SFO. So you can see they are using the GoGo in-flight and SFO Wi-Fi, and they are spending time at locations which are hotels and inns marked in yellow, and going to certain eateries. So this is again a segment of frequent business travelers. A similar component around the Los Angeles airport, wherein they land at Los Angeles airport and move into various locations in and around LA, and that is another business traveler segment. So we have POIs and we have connected component of POIs, and we have ranked the users against them. How can we now incorporate this into the business model of InMobi? I'll pass it on to Ian to explain that.
Hear me at the back? Yeah, thank you. So one of the things there which Seinjuti demonstrated was the two ways to kind of group users to kind of build out these segments, these kind of common behaviors. One of them was a static view, which looked at the individual kind of type of place where a person had membership. The second was more of the kind of dynamic view as people started to kind of pass through. But from our perspective, either approach will allow us to then suddenly have a define the membership criteria to belonging to a particular segment. Now with that we can then start to do comparisons between two different sets of users to see are there any kind of quirks or nuances to one set over another which we might want to try and take into account. So one of the ways to do this would be to kind of look at the app usage, so the actual publisher sites that send us the kind of ad requests. Are there any kind of differences between that, as in, do people have a tendency to use one type of application more than the other? And so in this, we've just shown a little table from a very sort of tiny subset of the data, just showing some university students versus the general population. General population defined as basically everyone who is not a university student. Then in the case here, we're actually seeing a kind of a slight sort of increase on productivity, health and fitness, lifestyle, when compared to the kind of university students. But they had a slight increase in terms of the amount of social media applications and the media and tools and so on. But just kind of going on to what we could then start to do is say, well, how does this kind of, what does this tell us if we actually look at this from a kind of dynamic time of day, almost a kind of context-based view? I'm not sure if you can read the labels clearly, but we've got the social networking style applications shown in blue, and then gaming in the orange and sort of entertainment in the grey. Across the x-axis is the hour of the day, running through till midnight, and then a sort of like normalized usage pattern. And so obviously we can see here when we look at the students that there's a kind of initial spike in the entertainment sort of around about sort of midday, but really the social networking application just increased steadily throughout the day. So we like to think that people are going out, living out their lives, and then kind of catching up with what else everyone else did in the evening. But if you were, say, an advertiser and you wanted to reach this particular set of users, you might want to kind of start to target this particular group of applications, social networking. And so we can see that on a weekday, that kind of is even more pronounced in terms of breaking down that style of usage. So this is just an example of how we can then take the classifications which were generated in the previous work by the location-based social groups and then start to kind of drill down into the analysis there. Just some kind of wider comments in terms of Spark, the usage of Spark and InMobi. So it's now become the platform of choice for data processing. So sort of all new tasks will be kind of written on kind of Spark. We have a lot of legacy Pig jobs, so being able to kind of use Pig on Spark is kind of great for kind of migrating that over. And on this sort of case-by-case basis, we're rewriting some of our kind of map-reduce applications to use the kind of Java API. And that concludes this talk, so thank you ever so much for your patience and listening. I'd also like to say a special thank you to Seinjuti for all of her hard work, and for a colleague, Paul Duff, based in Lithuania, for his hard work as well. Thank you.
We have some time for questions. Oh. Hello. I was just wondering how you exposed the SSID. Was that because of the ad serve capability of InMobi? You were able to see that?
So, yeah, so it depends on the publisher. So on the publisher, the people that own the kind of mobile property, if that is supplied to our SDK, so we don't grab it as such ourselves, which if we get kind of past it, we can utilize that kind of information.
The publisher made it available?
Yeah, yeah.
I heard a mention about some of the rebalancing copy on Spark, like the SMOTE.
Yeah.
Yes, so
Are you contributing it back to MLlib or you're keeping it in-house?
So we haven't finished the development yet, but we just realized that we need that feature. So if we are able to complete the feature, we'll definitely contribute it back to MLlib.
Hi, thanks for a very nice talk, and I especially liked how you guys were really upfront about the evaluation you were using and the improvements and sort of the trade-offs you saw with respect to that. My question is with respect to your evaluation. We do similar stuff, and we find it's, we have to take a careful balance between sort of held out data sets that don't change ever, which you can use to evaluate changes you make to your models conceptually or hyperparameters and features and so forth, versus data sets that are current with respect to what's actually going on in the world or the social world, or in your case the mobile world. So my question is sort of general, but how do you manage those two different kinds of evaluation requirements with respect to your models, with your model evaluation and retraining?
We generally when a project, it's normally the case that we do take a static data set and we just that becomes, and it's almost like trying to almost fail fast. Does the hypothesis, the reason for doing the work, does that seem to hold up and be true? Once we feel confident that is likely to be the case, then we would start to actually use, it would depend on a case-by-case basis, but we would want to start to actually use more recent data to make sure we were still having that positive effect. There are cases, obviously, when it can become more complicated and that you start to almost head down a path, and the new generate data that you're getting is actually better suited to demonstrate, so you can actually end up sort of skewing your results. Mm-hmm. So it's not perfect, but it's a mix of the two, and normally on like I say, a case by case.
Thank you.
We can take additional questions outside in the hallway then. Thank you very much.